we're going to look at some more examples of expected value. So remember, expected value is the average gain or loss of an event if the procedure is repeated many times. We can compute the expected value by multiplying each outcome by the probability of that outcome and then adding up those products. In general, if the expected value of a game is negative, it's not a good idea to play the game, since on average you'll lose money. It would be better to play a game with a positive expected value, although it would be tough to find one. Keep in mind that even if the average winnings are positive, it could be the case that most people lose money, and one very fortunate individual wins a great deal of money. If the expected value of a game is 0, we call it a fair game, and neither side has an advantage. So the first example we have here is of a card game, and you may have done problems like this before. A lot of you have. So I suggest pausing the video and seeing if you can do this problem on your own. So the question says, your friend proposes a game. You'll draw one card from a standard deck. If the card's a heart or a diamond, they'll give you $5. All right, so let's record that. That's one particular event. The event is we could get a heart or a diamond. And then the value of that event, if I make a little table here, is they're going to give you $5. So one thing to keep in mind is whose perspective that you're playing from. So this is the value from my perspective, not from my friend's perspective. His would be -5, right? If the card is a club, I don't want to draw a club, so I'll just write club. You'll give them $10. So that from my perspective, that's a -10. If the card is a spade, nobody wins, so the value is 0. So the expected value is going to be expected value, the value that something has, an event has, in the first event, $5, multiplied by the probability. So there, half the deck is hearts or diamonds. If I put the hearts or, meaning either or, that's going to be half the deck. The next event has a value of me losing $10, and the probability that I get a club is 1 out of 4. And the last one is 0. I could write it down, but it's not going to affect anything because I'm multiplying by 0. So the expected value here, let's see, half of 5 is 250 minus 10 divided by 4 is also 250. So the expected value of this game is 0. This would be what we call a fair game. If I play this with my friend, if we play long enough, law of large numbers, we're going to end up even in the long run. If we play it just once, you know, there's a pretty good chance, a 3 in 4 probability, that one of us will be ahead or behind. But if I play many, many, many times, it will be 0 overall average win or loss per game. All right, example B. A raffle ticket costs $3. There's one winning ticket out of the 150 tickets sold. The winner gets $300. What is the expected value to you of the raffle ticket? Again, you have to think about the perspective. So to me, what's the expected value? All right, so let's look at the possible events here. Now there's a couple different ways to do this one. Let's see if we can do it both ways. We'll see here. So one event is I win, and another event is that I lose. Okay, and what would the value be? So if I win, I'm going to win $270 because the raffle ticket costs $3 and then they're going to give me $300. So I'll win, not 270, sorry, 297. $297, right? Because it cost me $3. If I lose, I'll lose $3. So the expected value is going to be the value of winning times the probability that I win. What's the probability I win? Well, there's only one winning ticket out of 150, so the probability I win is 1 out of 150. The probability I lose is 149 out of 150. All right, so let's multiply this out. Remember, you have to do the division before the addition. Go ahead and pause the video and put that into your calculator. All right, so I came up with negative $1. So every raffle ticket I buy, my expected value is I'm losing $1. Okay, now there's another way to look at this. So the first way we did this is we kind of took the cost of the ticket and took it away from the winnings to get the $297. Another way to look at this is to think there's a 100% chance that I'm giving up $3 because I have to buy a ticket. All right, so if I buy a ticket, I have to pay that, right? So there's 100%, the probability is 1 that I have to pay $3 to buy a ticket. Now I could win $300, and there's a 1 in 150 chance that that could happen. All right, so if I do this calculation, I get, I'm paying $3, and then 300 divided by 150 is 2, and you still get negative 1. So you could do it either way. You kind of have to decide whether you want to think of what your payment is up front as a 100% chance that's going to happen, and then just do your winning, because your losing is already here. You've already dealt with the loss of your money by thinking of it as a fee to play the game, as opposed to up here, you dealt with the loss of your money by taking it away from your winnings. I know that's a little tricky, but it's kind of neat how it comes out the same either way. All right, well, let's look at a more real life kind of application, not just games. A 40-year-old man in the U.S. has a 0.242% risk of dying during the next year. An insurance company charges $275 for a life insurance policy that pays a $100,000 death benefit. What is the expected value for the person buying the insurance? Now, this is the expected value for the insurance company. It's for the perspective of the person buying the insurance. Now, this is a little bit weird because, well, if the person buying the insurance is the person that's insured and they die, then they don't get the money. But let's pretend like it's a wife buying a policy on their husband or vice versa. Okay, so let's say the wife, let's say this is the wife buying the policy on her 40-year-old husband or significant other, or I guess, you know, spouse, whatever. We could call it, let's call it spouse. Let's be more inclusive here. So we'll call it a spouse buying this life insurance policy on a 40-year-old man in the U.S. Okay, so we know, let's think of it like the raffle ticket, all right? We know that the spouse has to pay the insurance company $275. So there's a 100% chance that you're going to have to pay that $275 to get this life insurance policy. 100% chance. Expected value. So from the perspective of the person buying the policy, they're going to lose $275. But they could gain $100,000. Now, what's the chances they're going to get $100,000? Well, they only get the $100,000 if the 40-year-old man that's insured passes away. What's the chance that person's going to pass away in general for the insurance company, and of course it depends person to person, is 0.242%. Now, one thing I want to bring up here is these are the probabilities. And a lot of times when we're doing probability, especially when it comes to cards and dice and stuff like that, we write the probabilities as fractions. We could also write them as percents. We don't have to write them as fractions. Instead of saying there's a 1/2 chance I draw a spade, a diamond, or a heart, I could have said there's a 50% chance. There's a 25%. 1 in 4 is 25%. So a lot of times when you're dealing with these insurance type problems, the probability is given to you as a percent. So here we have it, guys. This is our expected value. and we just need to calculate it from here. So we know we're going to lose this, and then we take 100,000, 1, 2, 3 times, and you got to move that decimal 2 places. So you're going to end up multiplying by 0.00242. I got $242. So the expected value of this policy to the person is negative $33. Now, honestly, this problem actually makes more sense if we were to look at it from the perspective of the life insurance company. So the life insurance company can expect to make $33 per policy on this particular type of policy on a 40-year-old man. So even though they might have to pay out $100,000 to a spouse, they know in the long run they're going to be ahead on their premiums, what they're charging. And that's why they have to know these numbers. They have to know and these numbers change based on how old the man is, or maybe it's a different percent if it's a smoker versus not a smoker, or other factors like that, which if this number was higher, if there was more risk because there was a smoker or something, then you'd have to increase this premium to make it so that it comes out so the insurance company can make money. Now, remember, there's another way to do this, right? Just like this raffle ticket one, we did this 2 different ways. The way I did the insurance policy one just now was like this. I paid the premium up front, and then I did this part over here. But you could also do it as sort of living and dying. That's a little morbid, but I think in this case, it really makes a lot more sense just to do it this way. It gets convoluted to do it the other way, so I don't even think I'm going to show it. But if you feel so inclined, you could give it a try, and it should come out to be the same answer. All right, let's look at this last example, which is another great example of a real-life application of expected value. A company estimates that 0.3% of their product will fail after the original warranty period, but within 2 years of purchase, with a replacement cost of $500. If they offer a 2-year extended warranty for $40, what is the company's expected value of each warranty sold? So the idea here is they're going to charge a certain amount for a warranty, but if their product fails, they have to replace that item for $500. The company wants to make sure that they're not losing money on this deal. So they want to figure out, well, what's the probability that it will fail? All right, so the probability that it will fail is 0.3% of their products will fail after the original warranty period, but within 2 years of purchase. And if it does fail, they're going to have to pay $500. Okay, so those 2 things are going to go together. If they offer a 2-year extended warranty for $40, so this is a little confusing with the extended warranty. So there's some kind of an original warranty going on here. Maybe it's a year. We don't know. We don't care. All right, so we've got our purchase day. Let's say this is our purchase day. And then for the first year, 1 year, we get the original warranty. We don't have to pay any extra for that. Now, if you want, you can extend that warranty to 2 years. It's not 2 more years. It's extending this warranty out to 2 years. And if you do that, it's going to cost you an extra $40 to do that. So that's why it says the company estimates that 0.3% of their products will fail after the original warranty period, but within 2 years of purchase. So there's a 0.3% chance that that thing's going to fail between 1 year after purchase, but before 2 years after purchase. Okay. Now, if that happens, the company's going to have to pay $500. Now, we're looking at this from the viewpoint of the company this time, which is great. What is the company's expected value? All right, so if I'm the company, I'm thinking, well, there is a 0.3% chance I'm going to have to replace this thing at a cost of $500. So I'm going to lose $500, and there's a 0.3% chance that'll happen. Now, I also know that they're going to pay $40 for this. So I'm going to get $40 from each customer, and there's a 100% chance that's going to happen. Okay? So if I multiply this out, 0.3%, remember, is 0.003. So let's see, 500 times 0.003 is negative 1.5, and this comes out to be 40 bucks, so this is looking pretty good for the company. They're going to make $38.50 per warranty, extended warranty that they sell. I never get the extended warranty, but really if I was being more mathematical about it, I would ask what's the percent of times that it fails, you know, in that period, and then do the math and see if it works out for me. But I usually just don't buy it. So now again, for this one, you could do it the other way, and it's so hard for me to tell, you know, over video if anybody's thinking this way. But you could do it the other way and thinking as the company, either I replace it or I don't have to replace it. So if they sell this for $40, but it costs them $500, then they would end up, let's see, they would end up losing $460. And there's a 0.3% chance of that. Or they could end up just gaining $40, and there would be a 99.7% chance of that. So this comes out to be negative $1.38. This comes out to be positive $39.88. And if I combine those, I get $38.50. I'm kind of reluctant to show this way because I just think it's harder intuitively to think of it this way. But they're absorbing the $40 that they got into what they have to pay out. You'll get the same answer. I just think with these ones it's easier to think about it this way, with these kind of problems where you're either buying a warranty, or you're buying a life insurance policy, or you're buying a raffle ticket. I just think it's easier to say, hey, there's a 100% chance I'm going to have to buy this thing, and then dealing with the winning after that. But you don't put the losing in there because you already dealt with the losing by paying the premium or the cost of the raffle ticket. When it comes to card games or dice games or stuff like that, I would do it like this. Now, if it costs you money to play this dice game, then you're going to want to put that into your expected value as well. But these didn't. We just either won or lost. We didn't have to pay to play. All right, well, I hope that helps, and let me know if you have any questions on expected value.